You're on a remote site, and a new shipment of cement has just arrived. The bags look fine, but something feels off. How can you be sure it's up to standard before you mix it into your critical structural elements? The answer lies in a rigorous testing protocol. Cement is the backbone of concrete, and its quality is non-negotiable. Using substandard cement is one of the most expensive mistakes you can make, leading to weak concrete, durability issues, and even structural collapse. In this video, we're going deep into the world of cement quality control. I'll show you the key tests, from simple field checks you could do in 5 minutes to precise laboratory procedures that determine the final strength and stability of your structures. This knowledge is your first and most important line of defense in ensuring build quality. Let's start with the tests you can perform immediately, right on the job site. These are quick, qualitative checks that can raise red flags before you spend time and money on lab testing. The first is a simple sensory check. Good cement should feel smooth and cool when you thrust your hand into a bag. If it feels gritty, that could indicate improper grinding or the presence of impurities. Next, take a handful and throw it into a bucket of water. A good quality cement should sink and not float on the surface. Floating particles can suggest that the cement has absorbed moisture from the atmosphere and has started to prehydrate, losing its reactivity. Another quick test is the color check. Ordinary Portland cement is generally gray with a slight greenish shade. You can also make a stiff cement paste and create a cake with sharp edges on a glass plate. Submerge it in water for 24 hours. The cake should maintain its shape and gain some strength, not distort or crack significantly, which would indicate unsoundness. These field tests are not definitive, but they are your early warning system. If a batch fails any of these, you should hold it and send samples for laboratory testing before approval. Now let's move into the laboratory, where we quantify the properties of cement with precision. The first and most fundamental lab test is the fineness test. The fineness of cement grinding directly impacts its rate of hydration. The finer the cement, the greater the surface area, leading to a faster chemical reaction and higher early strength. We measure fineness using two primary methods, the sieve test and the Blaine's air permeability test. In the sieve test, we shake a 100-gram sample of cement on a 90-micron IS sieve for 15 minutes. The weight of the residue left on the sieve should not exceed 10% for OPC. A higher residue means coarser particles, which will lead to slower strength development. Blaine's method is more sophisticated, measuring the specific surface area in square centimeters per gram by observing the flow of air through a compacted cement bed. A pro tip from lab technicians: always ensure the apparatus is perfectly airtight, as even a small leak can give you a false fineness reading, leading you to accept a subpar batch. The next critical test is for consistency. This isn't about strength yet. It's about establishing a standard baseline for all other tests. We use the Vickett apparatus for this. The goal is to find the amount of water required to form a cement paste of standard consistency. This is defined as the depth to which a 10 mm diameter plunger on the Vickett apparatus penetrates the paste, placed in a mold, to a 0.5 to 7 mm from the bottom. The water percentage required to achieve this, typically around 26 to 33%, is called the standard consistency or normal consistency. This value is absolutely crucial, because all other tests like setting time and soundness must be conducted on a paste with this exact consistency. A common mistake is to use an arbitrary water-cement ratio for these tests, which will yield completely invalid and non-comparable results. You must determine this value for every new batch of cement you test. Now, let's talk about time-sensitive properties, beginning with the setting time. This determines how long you have to transport, place, and compact your concrete. We again use the Vickett apparatus, but with different attachments. We prepare a paste at standard consistency and note the time when water is first added. The initial setting time is found by replacing the plunger with a 1 mm diameter needle. The time elapsed until this needle penetrates the paste to a 0.5 mm from the bottom of the mold is the initial setting time. This is the point when the paste begins to stiffen significantly. For OPC, this should not be less than 30 minutes. The final setting time is measured by replacing the needle with a circular attachment with a central cut. The paste has achieved its final set when this attachment makes an impression on the paste, but the central needle does not. This indicates the paste has gained sufficient rigidity. For OPC, this should not be more than 600 minutes. A setting time that is too quick can ruin your pour, while one that is too slow delays construction and affects early strength. A pro tip for site engineers in hot climates: high temperatures can accelerate setting time, so you must plan your concrete deliveries and placements accordingly. Two of the most important tests for long-term durability are the soundness test and the compressive strength test. The soundness test determines whether the cement will undergo any significant volume change after it has set. This is critical because unsound cement will expand and crack, destroying the concrete from within. We use the Le Chatelier apparatus for this. We create a cement paste of standard consistency, place it in the mold of the apparatus, and submerge it in water at a specific temperature for 24 hours. We measure the initial distance between the indicator points. Then we boil the apparatus for 3 hours. After cooling, we measure the distance again. The expansion should not exceed 10 millimeters for most cements. This test identifies the presence of uncombined lime and magnesia, which hydrate very slowly and cause destructive late expansion. Finally, the king of all cement tests, the compressive strength test. This is the ultimate measure of a cement's ability to bear load. We prepare standard mortar cubes, typically with 1 part cement and 3 parts standard sand, mixed at a specified water-cement ratio. These cubes are cast in 6 millimeters molds, cured under controlled conditions for 24 hours, and then submerged in water until testing at 3 days, 7 days, and 28 days. In conclusion, testing cement is not an optional academic exercise. It is a fundamental pillar of responsible engineering. Each test, from the simple fineness check to the definitive compressive strength test, tells a part of the story about the material you are about to use to build your future structure. By implementing a rigorous QC protocol, you move from hope to certainty. You ensure that the concrete you place will develop the intended strength, will not crack due to unsoundness, and will set within a workable time frame. This disciplined approach to material verification is what separates the professional, high-quality project from a problematic one. Now I want to hear from you. Which cement test do you find most critical for your projects, and what has been your experience with a failing batch? Let me know in the comments below. If this deep dive into cement testing has been valuable, please give this video a like and subscribe to the channel for more content that builds your expertise from the ground up.